Hi, everyone. Thanks for coming, especially coming for the last session of the day, the session before drinks and going home. So this is our topics. Chao from IBM Research and I will present hyperparameter selection and adaptive model tuning for deep neural network. Here's why. I think all of you probably already in today's keynote, and Matei, the founder of Spark, actually did some manual tuning, ran a number of experiments so that he demonstrated to use the ML flow to track all the experiment. And here the goal is to automate the process so that we can improve the developer productivities, shorten the time to market, and also minimize the cost to create a good model, have a good accuracy in shortest time. So this is our agenda for today's talk. We will cover the first section will be presented by Chao. He will talk about several hyperparameter and network search method. Those are the ones we already implemented, and some of them already in the product, and some of them still in the research stage. And Chao will also compare all the different search methodology and provide the benchmark and the result. And after that, he will get into a topic for high-performance AutoML. You know the AutoML process is very expensive, quite often taking a lot of time, a lot of GPUs. Last Friday, I talked to a customer in New York. He said he spent 16 GPUs running for 2 months just to do a hyperparameter search of their a million image from their medical imaging data set. So high-performance AutoML is very key. We like to share some of our work and also result. After that, I will talk about interactive tuning during the training process. We want to provide good visualization tools and also provide a hint when to do early stop and advise user how to further tune the model. And we will definitely share some of the real-world experience and also share the implementation at the very end. This is essentially a chart to put into a picture what we're going to talk about. On your left-hand side, those are the presentation, how to do a hyperparameter search. The hyperparameter could include the learning rate, could include the decay rate, and then it also covered the network search. Network search, we talk about different layer of network, what layer we talk about, and also kernel size, pool size, things like that. And those things, automatic hyperparameter search and network search can be done in background through a batch mode. And the middle piece is more of interactive tuning and feedback during the training process. During the training process, we capture all the different metrics, statistics during the training. And later on, we use those statistics to determine the early stop scenario. For example, if there's overflow, if there's underfitting, overfitting, there's no point to continue. There's no point to spend multiple days running on multiple GPUs and wasting time. And then we provide advice to how to further tune the model so that the next run will be better. So those are the two dimensions, the batch way of a hyperparameter search and the network search, and then interactive tuning during the training process. I will hand over to Chao to talk about hyperparameter search and the network search.
Thank you. Now let me introduce the hyperparameter search and the neural network search, and it's also called AutoML. And we call it standard AutoML because want to compare with the transfer, the high performance AutoML. So the standard AutoML, we have implemented 3 methods from random search, Bayesian optimization, and the reinforcement learning. So we can find that the random search we implemented the hyperband, which is the multi-armed abundance method. You can view it as a balance between the exploration and exploitation, and it can be used for hyperparameter search, and it also can be used for neural network search. And the other is the Bayesian optimization. The Bayesian optimization, we model the accuracy, we model validation set accuracy or loss as Gaussian process, and select the acquisition function as exception improvement to maximize the exception, to maximize the expected improvement, and to use this to select the hyperparameter, to do the hyperparameter searching. And for the other part is the reinforcement learning. And the reinforcement learning can be used for the neural network search. It is a very hot topic today. And you can view it as the most important of this. This can be viewed as the Markov decision process. So the most important thing is to decide the states and the action. So we can define the states as the different component of neural network. For example, the convolutional layer with 3 kernel size, with 512 output channel, and with 5 kernel size. This is the basic component, and this is we can view this as the states. And the action is to link these states, link the basic module. For example, to link the convolutional layer with 3 kernel size with the polling layer with the 2 kernel size. So this is the action. So after define this action and the states, and we can use the Q-learning to select the model automatically. So this is we call the standard AutoML, and we have implemented it in our work, in our platform. And here is some result, and we can find that this is the hyperparameter search for object detection. And we can find that the adaptive random is the modification of, is the update of the hyperband. And we can find that from the best case point of view, it have best performance, but for the average point of view, and we find that the Bayesian optimization have the best performance. So the Bayesian may be more stable, and it is a big sense. Because the adaptive random search is maybe have the best performance in the best case, but it will have the low performance in the worst case. And here is the example for the neural network search. And we can find that this is an acoustic application, and we find that the default model is designed by the human expert, and we can find it's a 9 layers neural network, but for the reinforcement learning, it is modeled of 5 layers, and for the adaptive random, it is modeled 6 layer. So, and we can find that the lower the better. The lower is the error. Is the nominalized error, and we can find that the reinforcement learning has the best performance and is very stable from the CDF curve. Okay, And now let's turn to the high-performance AutoML. Why we do the high-performance AutoML? Because, as Yonggang mentioned, that there is a huge gap between the users want to get the user upload the data set and they want to get the best, the purple model, the best model in a short time. But when you start the AutoML process, it is very time-consuming process, maybe lasts for weeks or for months. So it is very high valued to consider the high-performance AutoML. Here we introduced the two methods. One is to use the historical knowledge to transfer the knowledge to speed up the searching process, and the other is use the fine tune and to reuse the weights, to do the fine tune. And now let's consider the first method. The first method, we involve the virtual data set layer. The virtual data set layer can group the different data set. So it can be viewed as a hard decision model sharing scheme, that all the data set in the virtual data set can share the same model. The model is the combination of the hyperparameter and the neural network. So this is our innovation. And after involve the virtual data set, and we can do the collaborative AutoML between the parameters, model, virtual data set, and their data set. And here is how it works. When the user upload the data set, and they can do the virtual data set group, which includes the white box analysis and the black box analysis. For black box analysis, we involve the benchmark model to probe the data set, to measure the similarity of the data set, so they can group the virtual data set. So if this data set is can belong to the existing virtual data set, and they do not do the AutoML process, they can reuse the model of this virtual data set. When it is not belong to, and it will do the AutoML process. So this is the basic idea, and we submit a paper in this year's NIPS about this work. So this works, the key component is to decide whether it can when and whether it can belong to one virtual data set. Okay, now let's turn to the AutoML with transfer learning, and we consider these two important parts to the combination of this. And training a small user data set, as we know, it will lead to the convergence problem. So when the user data set is very small, it is hard to convergent. So it needed to the transfer learning, and we can reuse the weights, reuse the neural networks and part of neural network. So when we consider the transfer learning, the pre-trained model need to be trained. You already in the CV domain, and we choose the ImageNet as the basic data set to get the initial weights as the pre-trained model. But from our experience, it cannot fit many specific user data set. So to solve this problem, and we can let user to classify its data set into the predefined category. For example, we can predefine a lot of category, the car, the train, and the landscape, and everything, and it let user to select. So this will involve the user's invention, and it's not a good solution. So we consider to using AutoML. So let's see how to use the AutoML with the transfer learning. Here we can see this is a Google Net, and to do the AutoML with the transfer learning, and we can reuse the inception in part, just tuning the at the last stage of the neural network and hyperparameter. By tuning this part of the neural network, we can adapt the data set with the network. All the parameters with the inceptions can be used as the initial weights, so it can deal with the convergency problem. So here is our searching space and researching the large states of the neural network and also the very large of hyperparameter. And here is some result, and we found that using the AutoML plus the fine-tune, or we call this transfer learning anyway, and we can find it always have the best performance. For the user-defined, user-small data set or the public data set. The action 14 is the public data set, and the other is the user data set, and we find that. So the transfer learning and AutoML can give the best accuracy and the most stable, and also do not need to separate the predefined, pre-trained model, so no user's invention. So that's our work about the AutoML, with the transfer learning or high performance or standard AutoML. Thank you.
Okay, so Chao just talked about the batch processing. You could run hundreds of jobs to do the background hyperparameter search and the network architecture search. And here I'm gonna show some a tool and a demo for interactive tuning during the training process. So what you're seeing here right now is our dashboard, and is that progressing? Yeah. And over there, it shows all the parameters, the network layers, but also monitored all the dynamic real-time metrics. For example, here show the histogram of the weight at the different layers. And of course, they show the accuracy and the loss function. And in addition, it also have a red button. Over there, it shows what's the current problem. And if the tool, this DL inside already detect early stop scenario, in this case, underfitting detected, there's no point to continue. And in addition, we also provide recommendation, and here in this case is add more hidden layers. And by doing this, you essentially avoid wasting a lot of time running useless training process. I'm gonna show a few more examples. So there is some classic traditional approach to detect the early stop scenario, but we did further enhancement. For example, in this case, if you use a traditional method, it will show this underfitting because there's a lot of fluctuation. But our method consider this is a good run because the learning curve keep going down. This is another scenario. If using a classic traditional approach, it will detect this is underfitting, but we actually consider this training should continue, and in the end, it's a good game. And here is another example. Initially, when we run this model against a data set, if you look at all the different layers, the histogram, there's arrows, there's zeros. It's an overflow scenario. We detect that and also provide a recommendation to change the cliff gradient to a different number. After the user follow the instruction and then change the hyperparameter, and the overflow scenario disappeared. And then there is another problem happen. This time is underfitting. And again, it provides a recommendation. And the user followed the recommendation, adding a few layers, and the situation become much better. Right now, everything looks good. After 900 iteration, it's still, accuracy is still going up. One more use case. Here is a data set from a customer. Initially, this is a small data set. And initially, it's not running very well because there's a divergence happens because a lot of up and downs. And then it provided recommendation to add more data. And actually, we did the data augmentation. We increased the data set. It had become slightly better, but still not desirable because the divergence scenario still detected. And we did the data augmentation again, and this time we add a few more pictures after tweaking. And you can see now the accuracy actually going up. So here, just a few scenarios is showing with this type of tools, the developer, the data scientists can improve their training productivity significantly. The capability, the integrity tuning capability, and also some of the hyperparameter search capability already as a part of IBM product offering. The product name is IBM Spectrum Conductor. This is the user interface. Over there, you just provide a range for learning rate, decay rate, batch size, and then select the different optimizer. And later on, we use a different search algorithm to come out a good set of hyperparameter. And the algorithm are already implemented in the product, support random search, Bayesian, and the tree-based pattern estimator. At the very bottom, you can see after we running many tuning jobs, and it provide a good set of hyperparameter, and which you can directly use during your training run. The way it's working is we support a shared cluster, multi-user, multi-tenant cluster. Over there, you can run a lot of jobs for different users, for different tenants. And for different search algorithm, we have a different strategy to launch those jobs in parallel, and then based on the previous iteration, the result of the jobs, and to determine how to do the search in the following iterations. As I said, we already implemented those three algorithms, and the other algorithm that Chao mentioned will be in future roadmap. This is just a very quick overview of the design, the backend design. What you can see here is there are multiple algorithms already implemented, and of course this is pluggable. And in future, we plan to open up the interface so that user can plug in their own search algorithm. And then we have model tuning manager, which essentially control the algorithm, the execution plan. And in terms of implementation, we actually use Spark to launch all those jobs. And with Spark, we also support different framework backend. At this moment, we support TensorFlow and Caffe. The PyTorch and other framework will come up next. And all those capabilities in a package, end-to-end package called the Spectrum Conductor Deep Learning Impact, and also work hand in hand with IBM Power AI running on IBM Power system. Over there, it has libraries, optimized the Power deep learning libraries available on Power. And then we manage the cluster, manage long-running service, manage all the jobs and the workload, and support Spark and Anaconda and all the different deep learning frameworks, and provide an end-to-end experience so that data scientists and the developer don't have to spend a lot of time doing routine work, copy data, loading model, VI, the parameter, and try to launch a job using R shell. They can just click a button and run the distributed learning job easily, and also leverage the capability we just discussed, hyperparameter search and interactive tuning to improve the productivities. There's some references. Definitely you can check. There's a number of algorithms we learned from paper working with our research partner from different universities. But we also have our own innovation. As Chao mentioned that we improved the Bayesian algorithm, we improved the hyperband algorithm, and we also came out with this high-performance auto ML. Of course, classic IBM disclaimer. And today, this session is the last session from IBM, and tomorrow there's more session from IBM. And if you have a further question, you can also visit our booth. We have a demo over there. We have 3 minutes left. We can open up for some questions.
Yeah, hi. Thanks for the talk. It was really nice. So I got a question about, so when you have these different hyperparameters and you're running different types of the models, how do you make sure that, for example, you do run a cross-validation on each of them, or do you set this exactly same seed? Or how are you able to compare?
Right. So there are 2 parts of it. One is you have a model, and then by using the search algorithm, you can come out a better set of a hyperparameter. And then you also talk about you could have a different model, and then you want to compare the result, right?
Yeah.
Right. So this is a two different process, and you could use say Bayesian to come out a good set of hyperparameter for one model, and then you can use the same algorithm to apply to different model, and then later on you can cross-validation and compare the result for your different model.
But then do you output sort of a confidence of, okay, this is better than the other one, because also you give a confidence, let's say this is 95 and 97 accuracy, and maybe the 95 has 2% of confidence, then you're not really sure it's actually better, right?
Yeah. So that's a good question. Right now we capture a lot of statistics across a different model run and also tuning run, and we also maintain a model database. Those things, what you just mentioned, could be further captured and also provide some statistics about the confidence level for different model. Anything you want to add?
Yes, currently our evaluation is among the 30 or 50 trials, different trials with different cross validation. So we think it can show the difference.
Okay. Can I ask another question? Yeah. So are we bounded to the models that you have in auto ML? So for example, let's say I want to include a Gator recurrent unit. Can I just do it, or am I bound to whatever auto ML models are in there?
You're talking about the search algorithm?
Yes, no,
You're talking about the model itself?
The model itself.
No, the model can be any model. Could be public
okay.
model, could be your own model, could be,
I missed that from
could be any model, and then you use this auto hyperparameter search capability, auto ML capability.
So I submit like a script? Yeah. I submit sort of a script that has my model, or?
Yeah, we have user interface. You click a button, you upload the model, and then you click, and then you select roughly the search space, and then you can also put a time bound, how much time you want to spend on search and how many GPU you want to spend on search.
If I have different models, the parameters can be different for different models. So
that's right.
So how How do I declare which parameter?
In that case, we have the user interface. You can upload the model, and you can instantiate a different model through model template, and then you could
you fill in.
Yeah, you could have a different tuning runs, and it will generate the good set of hyperparameter for each model.
I see.
Yeah.
Okay, thanks.
Okay,
All right, thank you, everyone. Thank you, Yonggang and Chao.
Yeah, thank you.